They move as if obeying a single command, as a single organism, but there is nobody who leads them. They are many, but they are one, a swarm.
The most fascinating thing about swarms is their beauty.
It's very difficult for us to understand a system without any hierarchy or central control because all of our social organizations seem to imply some kind of hierarchy.
How do ants manage to build a bridge? There is no order telling the ants to build a bridge or how to do it, but they still manage it. I'm interested in how masses behave generally and whether this can lead to a desirable result.
I think one of the things that's made swarm intelligence or collective intelligence seem mysterious is that it clearly operates in a different way from the organizations that we're used to. But that doesn't mean it operates by magic. It means that it's different and that we need to learn to understand how it works.
Swarms are different. The individuals are small and weak, but as a whole, a swarm has incredible abilities. Scientists speak of swarm intelligence. It comes from the collaboration of thousands of individuals. But can there be intelligence without consciousness? Scientists are trying to understand the mysterious behavior of swarms. We could learn from them. What seems alien and different at first glance could possibly even be very human. Sturnus vulgaris, the common starling. For Rome's inhabitants, an annual nuisance. Gigantic swarms overwinter between October and February outside of Rome's gates. At night, they look for places to roost in the warm city, much to the chagrin of its inhabitants. The daily spectacle above the holy city lasts around half an hour. These swarms contain up to 50,000 individuals. They create formations and break them up again, as if led by an invisible hand. It's a spectacle of the highest perfection, but there is no choreographer. The swarm is constantly changing its shape and density, but still, it stays together. There must be something allowing this extraordinary cohesion, a mechanism causing the swarm to organize itself.
There were many theories and models, but very few data to compare models with. So basically, everyone could come out with a new model, and everyone being happy about that because there was no empirical data to compare with. So this is what we wanted to do, to provide the first data on large groups of animals in 3 dimensions to validate or invalidate the models.
How does an individual bird have to behave so that the result is a perfectly functioning whole, a swarm that can't be ripped apart, not even by severe disruptions? The plan is to answer this question on a roof near Rome's Tamini station. Here, physicists from La Sapienza University want to uncover the secret of the starlings with a new method. They want to photograph the swarm with several synchronized cameras from different perspectives.
Standby off.
They hope to create the first three-dimensional images of these huge starling swarms. Using these photographs, the scientists want to solve a problem nobody has yet been able to answer. What do the individual birds in the swarm use as orientation? They want to find out how, from countless individual actions, a system is created that controls itself and makes collective decisions.
Swarms are phenomena where individuals come together in large numbers, and where those individuals orient themselves very strongly to the others in their immediate vicinity.
Im Schwarm sind, also ihre lokalen Schwarmnachbarn sozusagen.
The perfect synchronization of the movements is an aesthetic spectacle for us, but for the members of the swarm, it's a matter of survival.
Animals swarm for different reasons, and one of the most important is protection against predators. The risk of getting eaten by a predator is reduced the greater the size of the swarm. Another advantage can be when searching for food, because individuals get information from others in the swarm.
Das sind eigentlich diese beiden Faktoren, Räuberschutz und Hilfe bei der Nahrungssuche.
The swarm stays together without anyone orchestrating the movements of the individuals in it. It forms a unit that is greater than the sum of its parts. But the swarm also has to act all the time. It has to react to new situations and make decisions, such as whether to move left or right. Unlike packs, swarms have no lead animal that all the others follow. All individuals are equal. But how do swarms make decisions if nobody is in charge? This is the question that has been occupying behavioral scientist Jens Krause in Leeds for a long time.
The swarm organizes itself and can make a decision about the direction collectively. There don't have to be leaders to make these decisions for the swarm. The swarm organizes itself and can, as a result, make decisions about direction. But how are these decisions actually made? Because if you watch a swarm, it looks as if they all move at the same time, as if it weren't the product of many individual decisions. To understand this decision-making process is absolutely fascinating to us.
Das ist eigentlich für uns die faszinierendste Fragestellung.
Every individual in the swarm makes a decision. No single animal has the overview of the whole. The decisions of the individual animals produce the behavior of the entire swarm, and this behavior can be vital for the individuals. When a predator attacks, a member of a swarm has a much higher chance of survival than an isolated individual.
One of the key questions for us was to find how they can stick together in such large groups when they are heavily perturbed by a falcon, for example. So staying together for them is crucial. But they have to achieve this in face of very big perturbation. like change in density, in shape, and so on. So how they can do that. So we wanted to understand what kind of interaction between the birds, what kind of communication between the birds could give rise to this incredible capability of staying together of the group.
Andrea Cavana and his team have managed for the first time to depict a swarm of several thousand individuals in a three-dimensional image. The scientists are amazed by what they find. The birds behave completely differently from what had been assumed to date.
Before our results, there were many models and theories, and all models assumed that birds interacted in a purely metric way. This means that each bird is interacting with all birds within a given fixed radius. And this radius could be 1 meter, 2 meters, whatever. If this is true, then you see that in a high density situation, you are also interacting with a large number of individuals. While here you have perhaps just one individual interacting with you. So this is not very good to keep cohesion, because what these flocks are doing all the time is to change their density, like balloons which inflate and deflate continuously. So what we discover is that they do not interact in this way. So what they do instead is that each individual keeps under control a fixed number of individuals, of neighbors, irrespective of where they are. We find that they interact with 6, 7 neighbors. So in this case, this individual here, let's say, is interacting with these 6 guys. And then in this case, it is interacting with these guys, irrespective of where they are and how distant they are. So in this case, in the low density flock, they will be pretty far away. In this case, the high density flock, they will be very close. While in this case, they're rather distant because of the density. And so you see it's completely different from a metric way of interact.
So it isn't the distance that is crucial for a swarm's cohesion. It's the number of neighbors with which a bird communicates. The simple behavior of the individuals results in the complex behavior of the swarm. This allows swarms to adapt to ever-changing situations and also to solve complicated organizational problems, such as those of the red harvester ant in Arizona. They are not even a centimeter in length, and they are blind. But there are many of them. A single colony of red harvester ants numbers 10 to 12,000 workers. It takes a second glance to recognize their nests, flattened mounds protruding gently over the desert floor. Red harvester ants mainly eat plant seeds. But only some of the ants' work is related to gathering food. There are many other tasks that need doing in a colony. Some keep the nest in order, others take care of the young, and yet others remove rubbish. All of these activities have to be coordinated to allow the collective to survive. No individual ant has the overview over the condition of the entire colony, not even the queen.
When humans set out to do something collectively, every person has some idea of what the goal is of the whole group. And what's amazing about the way that an ant colony works, there's no ant in there that says, we need more food, we need to work harder. Each individual, each component uses only local information and makes very local decisions, and in the aggregate, the whole system works. But no participant in the system understands what needs to be done.
Armed out of the entrance? Yeah.
The complex division of labor of the red harvester ants is a mystery Deborah Gordon has been investigating for decades. Together with undergraduate and doctoral students, she leaves her laboratory in Stanford University every summer to set up camp in southern Arizona. Here, close to the Mexican border, she is researching how colonies of red harvester ants organize their lives and work. Unlike the myth of the ever-busy ant, the ant colony is not equally active every day.
A colony, like any organism, has to respond to a changing environment. Things happen. One day there's more food, one day there's a storm, and the nest has to be repaired. And somehow the colony has to change the numbers of ants working on each task in a way that's appropriate for the current situation. And the question that I ask about harvester ants is, how does the colony do it? If nobody's saying, okay, we need more over there fixing the nest, or we need more over there collecting food, and yet somehow the colony does adjust its effort to different tasks. So my question is, how do they do it without any central control?
Nobody tells the ant colony what to do, but it still acts as a coordinated system. It is the collective that decides. But how are decisions made that are supported by all of the members of the group? Does it matter how large the group is? In order to find that out, Jens Krause brought in assistance.
We developed the robofish in order to have total control over one fish in a swarm. This has always been my dream. I came up with the idea when I was 18 or 19. You can see how a swarm makes decisions, but you don't know which fish initiated this decision. But with the robofish, we have a way of creating a decision. We can decide when a fish turns left or right, and we can then see how the rest of the swarm reacts to this decision. This gives us a very controlled situation in the aquarium.
The robofish is controlled through a magnet under the aquarium. The real sticklebacks are suspicious of the stranger at first, but then they accept it as a member of the swarm, despite its strange behavior.
The robofish moves the way we tell it to. A normal living fish would make a directional decision, and if others didn't follow suit, it would quickly return to the swarm and adapt. But the robofish doesn't adapt. That's an unfamiliar situation for the other fish. Members of the swarm don't usually make such extreme decisions. They tend to then follow this individual because they assume it must have very clear information which it is acting on at that moment, and this has a very strong influence on the others.
The researchers want to conduct an experiment to find out how individual decisions become collective. The experiment involves a swarm making decisions. It has to choose the best option when presented with several. To stop it from being too easy, the robofish is made to incite the others to a behavior they wouldn't normally pursue. It is attempting to lead them away from the worms. At first, the test swarm is too small. Only 2 fish are in the aquarium with the robofish. The robofish easily manages to move the swarm away from the food source. The swarm has allowed itself to make an unfavorable decision.
Right. But yeah, they like to cut this corner.
They really do, yeah.
The experiment is going into the second round. Now it is 1 against 10. The robofish will behave in exactly the same way as in the first experiment. The question is whether a larger swarm is just as easily manipulated as a small one.
Okay, let's run it.
The larger swarm also follows the robofish to the food, but it can't get them to move away. The swarm has overridden the decision of the robofish and made a different, more intelligent choice.
In a situation where a leader fish makes a bad decision, the swarm will not necessarily follow it unless this decision is supported by one or two other fish, which makes it more convincing for the rest of the swarm. We talk about threshold values. A certain percentage of the swarm has to perform the behavior for the rest to follow. One individual isn't always enough. That makes sense because individuals can make bad decisions, and this principle of social rankings prevents that, which is a form of swarm intelligence.
Swarms behave more intelligently than individuals. Their ability to solve problems and make decisions can be classed as intelligence. It's an intelligence individual creatures don't have. This intelligence is created as a result of the coordinated behavior of the individuals. This swarm intelligence must also be what allows the ant colony to adapt its activities to the day's requirements and to decide whether it is a good day for foraging or not. Before the foragers of the colony become active, patrollers explore the terrain for food. It is only when they come back that the others start bringing it in.
Most ants can't see. They operate mostly by smell, and ants are coated with a layer of grease that carries the colony-specific odor. And that's how any ant or bee or wasp knows when it meets another ant if it's a nestmate, because each nest has its own characteristic odor. And then we found that in harvester ants, at least, each task has its own odor. So an ant that spends a lot of time outside, like a forager, ends up smelling different from an ant inside the nest.
A forager recognizes a returning patroller by her scent. But that's not enough to cause her to leave the colony, because the colony first has to calculate whether it is safe enough to deploy foragers. Working in the desert is perilous, after all. What tells these ants when the right time to gather food has come? To find that out, the scientists use the scents of different workers. The scents are applied to small beads the size of ants. They are fake ants designed to trick the real ones. Gordon and her colleagues want to find out what mechanism the colony uses to organize its search for food. As expected, only the beads with the patroller scent stimulate the waiting foragers to begin searching for food. But it takes another, more sophisticated mechanism to explain why on some days thousands, but on others only a few dozen or no foragers set off to work.
We found that foragers wait for patrollers to come back before they go out to forage. And the foragers won't go out until they meet a patroller at a rate of about 1 per 10 seconds. So we tried dropping in the beads too fast and too slow, and it has to be at an interval of about 10 seconds. And that must be how long an ant can remember what happened to it. If an ant meets another, say, every 45 seconds or every 60 seconds, it's as if it never happened. It's forgotten that it ever met the other ant.
Only when sufficient patrollers return safely to the nest do the foragers set to work. That's how, unlike an individual ant, the colony knows whether it's a good day to search for food.
The more I study ants, the less I think is going on in the mind of an ant. So the system has become very familiar to me, but what it's like to be an ant seems more and more different from what it's like to be me.
Simple units that, as a group, form an intelligent whole. It's an intelligence that isn't controlled by a central brain, but by an acting together of many non-intelligent individuals. The swarm's recipe for success fascinates biologists, but in recent years it has also captured the attention of engineers and cyberneticists. Their idea is to apply swarm behavior to machines. This is the birth of robot swarms.
The science of robotics is interested in swarm intelligence because it makes it possible to control many robots without central command. In the 80s, many engineers asked themselves how to construct robots that would also function reliably in a constantly changing environment. The traditional methods in robotics proved unsuccessful in this regard. The robots were extremely susceptible to problems and hardly able to react in real time. That's why in the 90s, people started to go down a completely new route in robotics. Instead of building a single, more complicated robot, the idea was born to build robot swarms, consisting of individuals with a very simple behavior, but with the ability to solve problems together.
The biologist Guy Terrolas is researching how insect swarms solve complex problems and how the strategies used by ants can be applied to artificial intelligence.
The behavior of ants is very simple. They are living machines, of course. They're very complex machines, but their behavior is very simple. Every ant only has a repertoire of around 20 different behavioral patterns.
There is one simple but ingenious ant strategy that has inspired robot designers more than any other. The method different ants use to exploit a food source as efficiently as possible. This experiment shows how it works. A colony of black garden ants is supposed to choose in favor of the shorter of two routes between the nest and the food source. Which route the ants pick first is completely random. No individual can estimate or even measure its length. At first it looks chaotic, but after just a few minutes, something incredible happens. The colony decides collectively to opt for the shorter of the two routes. This is made possible through a special information system.
Ants, as insects, can take in complex chemical information known as pheromones. This gives them access to signs we, as humans, can't read.
Ants give off pheromones, scents that evaporate with time. They follow a simple rule. When in doubt, they take the route that has more pheromones. This rule triggers a simple but ingenious mechanism. Ants that just happen to take the shorter route first return faster. The shorter route gets a higher pheromone concentration, so more and more ants setting off choose the shorter route.
This is a real example of collective intelligence, because individual ants aren't capable of measuring the length of the route. They can only do this together, so it's a collective phenomenon.
Like the ants, the mini-robots are rather helpless as individuals. They only possess a few sensors and a few basic behaviors. Like the ants, the robot swarm has to find the shortest line between 2 points. First, the robots search the network randomly. They don't know where the goal is. Like the ants, they are programmed to follow the light traces of their colleagues. The brighter the trail, the greater the probability that a robot will follow it. The robots recognize when they are in the start or destination zone. It's only now that they themselves begin to release messages. Over time, the light trail between the start and goal becomes stronger, and the other trails fade. After around 20 minutes, all of the robots are on the shortest route. The ant strategy has worked here too. Robot swarms are still in their infancy, but great tasks await them.
There has been much discussion about possible future applications for robot swarms. One of them is the exploration of hostile environments, such as other planets. Another area involves nanorobots injected into the body. In such systems, individual components would be tiny and, as a result, so simple that individual robots couldn't be controlled. The only way to control such systems would be to use the interaction between the robots.
The future belongs to robot swarms. At the University of Stuttgart, researchers are going one step further, from swarms to organisms.
The vision is to create the self-organization of individual components without explicitly programming this self-organization. Imagine a member of a swarm is actually a cell in an organism. Then you can imagine a robot swarm coming together, as a dog maybe. This dog will be able to overcome obstacles far better than an individual cell.
The swarm has to adapt to its environment. It has to develop to survive.
Imagine our swarm is released on inhospitable terrain. Say I deploy 100 swarm robots in rugged terrain where they could only survive if they came together as a single body, by forming a snake, for example. As a snake, they could then survive.
The artificial organisms of the future will program themselves and share their energy and information, independently and without human control. The aim is to have the robot organisms adapt spontaneously to new tasks, without it being necessary for their developers to program them first.
That's exactly what evolution has done. It wasn't all controlled from above.
A machine evolution in fast forward. How this could work in the future is being researched here by using small swarm robots, the predecessors of the future robot cells. What is happening here is robot sex. Strategies are being tested with which the robots can pass on their genetic information. The population that is better adapted dominates, as in natural evolution. For computer scientist Paul Levy, this is also a further development of intelligence.
It is possible to imagine that a swarm which is capable of taking care of itself will automatically seek out new tasks, and that the same swarm can solve further problems by looking for new, better territories where it can support itself better. That's conceivable, and that's an increase in intelligence.
Das ist für mich schon eine Steigerung der Intelligenz.
Intelligent robot swarms that don't need human supervision are still a vision of the future, but it is also one that troubles many people. What about humans? To what extent does our behavior differ from that of swarms? We act as individuals. We decide rationally, independently, and of our own free will. That's what we think, anyway. But do we really act as individually as we always think? Or do we too, unbeknownst to us, follow swarm logic?
I became interested in the extent to which processes in society could be understood using concepts from complex systems from the world of physics. These systems consist of many components, such as gas or liquid particles that interact with each other. In physics, you often find structure-forming phenomena, such as waves or turbulence, and the same thing can be observed in society.
Und Ähnliches kann man eigentlich auch in der Gesellschaft beobachten.
Physicist Dirk Helbing has been researching the dynamics of pedestrian masses since the 1990s. For the untrained eye, this is just chaotic disorder.
It is very interesting when you look at recordings of pedestrian masses in fast forward, accelerated 10 times for example. You can see that the chaos isn't as great as you initially imagined, because then the brain becomes capable of recognizing patterns.
In dense crowds, movement patterns, structures form that we as individuals are not aware of. Nobody controls these patterns. They form by themselves as the result of countless individual actions. They are structures by which crowds regulate themselves without individuals taking deliberate action.
Many self-organization phenomena that form in pedestrian crowds actually optimize the flow of pedestrians. Local encounters between pedestrians lead to evasive maneuvers, and all of them put together produce an intelligent result, where the different movement directions are separated.
Our behavior is controlled by collective dynamics. Individuals are not usually aware of these dynamics. But the result of self-organization isn't always intelligent. Traffic jams are also the result of such processes, as are mass panics. In 2006, a disaster occurred amongst Muslim pilgrims in Mecca, causing almost 400 deaths. Eddy-like patterns formed, structures with a huge force. Individuals were completely at their mercy.
Self-organization processes can also produce unfavorable results. More research is needed because we don't know under what conditions this principle works and under what conditions it doesn't work. What causes undesirable results?
The calculation of self-organization patterns in crowds could help avoid such uncontrollable situations in the future. Humans physically demonstrate the processes that resemble those of swarms in certain conditions. But do we also demonstrate swarm behavior in our thoughts? Is there really such a thing as the wisdom of the many? One experiment in Zurich is examining for the first time whether people's decisions can be controlled by collective dynamics and whether they really are smarter together. 20 test subjects have been asked to give an estimate. The closer it is to the actual figure, the higher the winnings at the end. First, all the participants have to give their own estimate, but they are all connected to the other participants. After every round, the test subjects can see on the screen what values the others gave. If it turns out that the average of all the estimates is better than the individual estimates, there really would be such a thing as a wisdom of the many. If the principle of collective intelligence were to work in humans, it could be applied in useful ways, in business and society. But the result of the experiment is less clear than expected.
We found out in our experiment that there is a collective or swarm behavior. The question is the behavior favorable? Do we get a wisdom of the many? Our result is deflating. Sometimes the group identifies the correct solution, but sometimes it is way off. So we should be careful about relying on a wisdom of the many.
Whether the collective is really wiser than the individual is something nobody can yet answer with certainty. But what is certain is that human beings also behave like a swarm when making decisions. Not always, but more often than we think. We have been led by the notion that intelligent behavior has to be controlled by an intelligent consciousness. But strategies for success on the part of swarms show that that's not the only way. It's a kind of intelligence that seems strange and alien at first glance. But in truth, it's closer to us than we think. We can learn a lot from it, and we've only just begun.